So we'll continue on with our program with our first tutorial speaker. It's Professor Yolanda Gill from USC talking about the Geosciences paper of the future, practical guidelines for adopting digital scholarship, reproducible research, and open science. Dr. Gill.
Thank you very much for welcoming me here. I'm very excited to spread the word about the future. My research is in artificial intelligence. I'm very concerned about the future. I try to build systems that assist scientists and automate the parts of science that are really boring. So that's my day job. And part of that is to see how publications and scientific publications can be more accessible to machines. And right now they are not. So I'll tell you a little bit about that and the motivation for the geoscience paper of the future. What I'm going to talk about today are best practices and guidelines that you can all implement to make your papers more accessible, not just to my machines, but to your colleagues and people in related disciplines. So I'll talk about digital scholarship, reproducible research, and open science. This work was part of, or is part of the EarthCube initiative at NSF. It came out of the OntoSoft project that I lead, and also the InGeo, the Integrated Geoscience Observatory, led by SRI. I want to acknowledge contributions from dozens of people, many scientists that have contributed to the ideas, the best practices, the caveats, the way that we present this material, and in particular to Asti Bhatt for putting this together as lead of the InGeo project, and to Aaron Ridley, who volunteered as a way for us to look closely into one of his papers and put it under the microscope to give you better examples. So to give you an idea of what scientific papers look like today, I'll give you an example from a study that we did. We took a publication from Phil Bourne. Phil Bourne was the assistant director for data science at NIH until earlier this year. He came from UCSD, and he's a proponent for open science. He was one of the founders of PLOS, the Public Library of Science. He makes all of his research data, proposals, papers, everything available publicly and openly. And we set out to reproduce one of his group's papers. It took about 2 months of work, and we found that we really needed the author's expertise to do this. So to give you a quick example, the paper had text that said the SMAP software was used to compare the binding sites of protein structures plus homology models with all the binding sites of approved drugs in an all-against-all manner. That's all it said. We thought it was a run of the SMAP software doing all this, and actually, they ran the SMAP software 2 separate times with 2 different sets of pairwise comparison data. Then they merged the results, they sorted the results, and they filtered results that were under a certain threshold. None of this was discussed in the paper. And in fact, we built what you see on the right, those colored squares that we call reproducibility maps. And you see that there's some of them that are in red and some of them that are in green. In green, it means that at that level of expertise, you could actually reproduce all the steps. And there's a lot of things in red for good reason, because throughout the stages of the paper and the method in the paper, only the authors or people at their level of detail and expertise were able to reproduce the work based on what the paper said. So this is the state of the art in publications. So if I want my AI machines to read this paper and make something out of it, it's a little bit impossible to reproduce these computations and hypothesize these computations just from the text. Another big problem with current practice is that is the access to data, the data used in publications. So the data is often not shared. Sometimes the papers say, contact the authors if you want the data. There's been a lot of studies where even if the authors are contacted, the data is not easily found or perhaps never returned. The amount of papers where the data is not available or they're hard to reproduce or impossible to reproduce is really staggering. Also, many times we make data available or software through URLs, our lab URL, our university URL, and oftentimes those URLs rot. So they are no longer operational. And so I'm citing here a paper that one out of 5 articles has reference rot after just a few months. So this is not a very good way to publish papers that are supposed to be archival and durable. So publishers are really concerned about this, and they're really changing the way that they allow authors to publish. So you will see encouraging publications about data sets that are important and reused throughout the community. You see new journals about describing protocols and methods. You see software publication requirements. You see all kinds of instructions about where can you put data so that it's safely accessible as your paper ages over time. So the publishers are really changing. They don't want to publish garbage or papers that really the contents or the work is not very, is not something that others can build on easily. Reproducibility is also a concern. I'm sure that you've all seen all kinds of news items and discussions on this. I'll just highlight this survey at the top right done by Nature, asking scientists if there is a reproducibility crisis. And the majority said yes, and then a whole another 38% said yes, a slight crisis is not horrible, but there is one. So there's all sorts of concerns about making science reproducible. Because science affects policy, a lot of the funding agencies are also concerned by this. So I was at a AAAS Science and Technology Forum meeting earlier this year where different funding agencies were showing their new policies to ensure scientific integrity, reproducibility, and open science. And these policies are not going away. They want to make sure that policymakers can trust the results that come out of these agencies. So you see here reports and guidelines being developed by all the agencies that you can imagine in the government. Not just agencies, but the scientific community is also acknowledging integrity and reproducibility as very important. So from the government to publishers, but also scientific associations. There's new community groups like the Research Data Alliance, Force 11. There's also a lot of new efforts to save data. COPDES, for example, on the bottom right is an association with hundreds of publishers to ensure transparency, data access, open publication throughout the geosciences. There's a lot of different efforts and organizations really concerned about the openness of science and making sure that our publications are follow digital publication practices, best practices. Scientists are also changing, so we all expect that things are free, we all expect open software, we all expect the data to be available. There's a lot of scientists leading efforts to create repositories to make sure that credit is given to data collection and data producing entities and authors. Metrics of impact that are based on software that we produce as scientists. So science is also changing in this respect of making it more open, giving credit to people, and so on. Universities are also changing, recognizing the increasing role that computation has in science and the need to have a strict and rigorous methodology when you follow computation in computational analysis and scientific papers. So there's a lot of different initiatives in major universities towards this end. So what are these best practices? That's what I really want to talk to you about. These ideas are not going away. I gave you all this introduction so that you see that this is really going to stay, and it's pretty pervasive in all the different stakeholders of science. What are these core recommendations? So what I'll do is I'll summarize them briefly, and then I'll give you examples of them so that you can see in much more concrete ways what they are about. So they center around reproducible research, open science, and digital scholarship. So if you want your computational analysis to be reproducible, you have to expose your data sets, the software that you're using, and all the steps that you're following, no matter how minute they are, into a workflow or data flow of computations, and what are the outputs of some computations that go to other computations. Some of these steps may be manual steps, so you may filter out some outliers, or you may do some adjustments by hand, but you need to document those steps as well. And something called experimental design. So how many data points did you use? How did you design a statistically sound analysis? So all of these components are key to experimental reproducible research. In terms of open science, the first thing we worry about is to make sure that your data and your software are in shared repositories. So my field is artificial intelligence. Most researchers put their software in their personal website, so there's a personal URL. If they move to a new university, that site is completely lost. Same thing with data sets. They tend to be in some lab website, and they get lost. So the first thing to do is to preserve your data and your software in shared repositories, and there's many of them. Zenodo, for example, is a data repository run by CERN. They keep increasing the limits of the size of the data that you can upload to it. They'll take data, they'll take software, they'll take slides, they'll take movies, graphics, anything, any products of scientific research. Dataverse is a big data repository out of Harvard. It has a constellation of different sites throughout different universities. So a lot of universities are doing their Dataverse site where researchers in that university can upload data. And lots of universities have their own ways to deposit data. GitHub is very popular for software, but in geosciences there are repositories for computational models that are specific to geoscience. So whether discipline specific or generic like Zenodo, there's a lot of resources available to you that are free to use and that let you share your scientific products with others. Another important thing is persistent unique identifiers. So URLs not allowed, you'll move, the URL will change, not a good idea to put that in a publication. We want to see a persistent URL, which is something where you redirect, and it's in a central repository. And most of all, most people use a DOI, a digital object identifier. So you can assign DOIs to data sets. You can assign DOIs to software versions if you use any of these shared repositories that I talked about. So these are best practices. You can also assign unique identifiers to samples, physical samples. And finally, your data and your software should have a license associated with it. So if you have any concern about your software being taken over by the commercial world, there's licenses that allow you to share it for research purposes and don't allow anyone to commercialize or use it for commercial purposes. There's other kinds of licenses that will allow any kind of sharing. So you can choose your license. Same thing for data. Data is typically assigned a Creative Commons license, and software and open source license. So these are important pieces of making science open, making sure that it's in a shared repository, that you have an identifier that will reach it right away, and that when somebody reaches that data set, they understand what they can do with it, or data set or software. The third big area is digital scholarship. So By that, we mean that we're used to citing each other's papers. We're used to credit each other for research that we build on. But we're not so used to crediting people for writing good software, for contributing data sets to the community, and so on. So in digital scholarship, modern digital scholarship, you want to have citations for data and for software as part of your paper. So a citation for a data set looks as follows. This is one of our data sets. You have all the authors, the year, you have a name for the data set, and you have the name of the repository where the data set is. In this case, it's called Figshare. It could be Zenodo. You have the URL or the DOI, and then the date of retrieval. The example at the bottom is a citation for software. So it's just included in the references section of the paper. And the only thing that's different for software is that you include the specific version number. And each version of the software should have a DOI associated with it. So these are best practices of digital scholarship. I'll give you examples of all of these as we go forward. So all of these best practices, I go to lots of meetings, talk to a lot of people that are generally concerned with these topics, but these best practices don't easily reach science and research audiences like this one. So to remedy that, we founded, as part of EarthCube, the Geoscience Paper of the Future effort, where we try to highlight why reproducibility and open science and digital scholarship concerns should be adopted when we write papers. And this initiative had two aspects to it. One, a special issue of a journal where you could actually see exemplars. And these papers would actually describe how they address these best practices and in some cases why they were difficult. So you will see examples of these papers where the author discusses that a colleague did not want to release a certain data set because they were writing another paper about it. So the data set would be released at a later date. Or the size of the data set was too large, and so on and so forth. So these exemplar papers are a frame of reference to see lots of examples of how to do papers in this way. And then we've also held a lot of training sessions throughout different conferences, different institutions. So if you go to this website, you can see a lot of examples of that, and we're always open to do more. These are the pioneer authors. They're all early career researchers that we approach to advise us on how to best put out the word about the paper of the future. They had a tremendous amount of input on what best practices were reasonable and which ones were kind of long-term things that I'll have to worry about next summer when I have more time to worry about those topics. But they all identified simple things that you can do to improve the paper that you're writing right now to make it better. So if you look at that special issue, there's papers on different disciplines, and there's actually a paper written by all of us summarizing all the best practices that I'm skimming through in this talk. So if you really want to go deeper or you're curious about a particular repository or recommendation, you can read more and have more context in that paper. So what does one of these papers of the future look like? I'll give you just a quick example, and then I'll go into more depth using Aaron's paper as an example. So this is a paper from geology. The actual paper had text like this. I've hidden the name of the authors because I had to embellish the text a little bit. So they took a quartzite sample, cut 3 thin sections, measured z-axis orientations through a microscope, rotated to a common reference frame using the StereoNet software, and then plotted certain things using that program as well. And the results are shown in a figure. So what this tells us is that there was actually a workflow of steps that were followed, taking measurements first through the microscope that produced the z-axis orientations. The rotation was done. There's a little bubble to the top right of that indicates any parameter values that were used to do that rotation, and so on and so forth. So having all these steps explicit really helps because sometimes in the text you may omit some of them. And what the paper would look like is that the paper itself will have a DOI, as all papers do. The author would have a unique identifier as well. These are called ORCIDs. That's the one that all the publishers are adopting. So each author has a unique identifier as well. The quartzite sample is given a unique identifier. The C-axis orientations are deposited in a data repository. The common reference frame, the software, the StereoNet program, all of these steps have their corresponding DOIs. And so throughout the workflow, you can see that we're assigning DOIs to the software, to the input sample, to any intermediate data that we think are important enough to publish. And then at the end, the figure is shown, but so is this provenance or workflow for the results. So that's what a modern article looks like. The DOIs are not actually there. I just want to show them so that you can connect them. It would be a citation. The citation would then describe the authors and all the details, including the DOI. But just to give you a concrete idea. So by doing this, all of these identifiers would lead you to the actual data, to the actual software, and you can actually see all the steps very clearly. A lot of the GPF authors tell us that when they try to sketch these workflows of steps with all the software, they realize that their software is not broken up properly, that the parameters are not really accessible properly, that they've forgotten to include some pieces of the workflow. So it really helps really report the computational aspects of the work a lot better. And I've had some PIs also say, now I know what we were doing. So if you have 4 or 5 authors, it's kind of hard to tell. And when the workflow gets a little bit complex and has many steps, they'll say, now I know why we needed that guy to do this thing and why you guys were meeting all the time. So think about the traditional articles as having just the text. More modern articles often include the data, supplementary materials, and so on. And then very rarely is the software really included. Especially, we think of software as a big model or a big piece of code. We don't think of scripts that we do to transform data or to plot data and so on. And these are very important to make the work more reproducible. So reproducible articles will include all of the software in addition, and these workflows and provenance descriptions. Reproducible publications are becoming very popular, so there's a lot of different tools and software and frameworks. A lot of people love notebooks because they help you keep the data, the software, and the story that you tell about them all together. The first computational reproducibility framework that I know of was done by John Claerbat at Stanford in the 70s and 80s in his CEP research group. And that work continues at UT Austin with the Madagascar project. So as geoscientists, you should be very proud that your field pioneered computational reproducibility. So there's a lot of different frameworks to address reproducibility. The kinds of things that I'm talking about today are beyond notebooks or workflows or reproducible papers or executable papers, whatever terminology is used. We want to push for these, making the research not just reproducible, but also open and making sure that we take into account digital scholarship concerns for citation and metadata. So I wanted to connect with the way that you write papers, and so I asked Asti to suggest a good paper from your field, a representative paper from your field, and she suggested this one, and Aaron was kind enough to allow us to put it under the microscope and help us through it. So it's a paper on simulating electron and ion temperature in a global ionosphere-thermosphere model, validation and modeling, an idealized substorm. I read this paper beginning to end. I have no idea what it talked about. But computationally, it made it very, very clear for someone like me looking for computational breadcrumbs that it did 3 major things. One is to present a new version of this model, GIDM, and it did a comparison with a previous version of the model. It also did a comparison with another model, IRI, for several sites, and then it looked at how the model addressed an idealized substorm. So to me, these were three major computational efforts that were included in the paper. So I'll show you, just like I showed you at the beginning, that biology paper, what the text looked like and what the computation might look like and so on. And I have to say, I was pretty impressed that I was able to at least follow what was done in this paper. That's not the case with most biology papers that I read, and I read a bunch yesterday on the plane. So I have to say, this is a much better discipline to look at from a computational perspective. So let's look at the data first. So quoting from the paper, it says, figure 1 shows comparisons using the old model, the new model, and IRI at an altitude of this on that date. The data is not there, and as I understand, the data is provided through CCMC when you run the model on demand. So there's data about brightness of the sun, strength of the aurora, electric fields that come from NOAA, NASA, and there's other data as well, but this data is not included or cited in the paper. So other disciplines in geosciences have repositories that actually will give you a DOI for whatever data set you're downloading from that repository so that you have a unique way for others to access the same data set. The paper goes on to talk about a substorm, a simulated substorm, and there's a separate paper that has the substorm data and plots to it, but the data itself is not cited. It's the other paper that is cited. So best practices would say that that other paper plus this paper should all cite this data set, and anyone else who's using that same data set should cite that data set, that particular substorm, and all the data should be together somewhere. So to run over the best practices, all the input data should be in a public repository, and any important intermediate data. So when you reproduce a piece of work, if someone wants to compare the new GIDM model with their own, when you reproduce a piece of work, if you don't have intermediate data, you may not be sure that you got all the parameter settings right, and so on and so forth. So I know that there's community repositories that you all use, like Madrigal. There's university repositories, like I mentioned, Dataverse. There's other general repositories like Zenodo. Whatever data repository you use, they'll give you a unique identifier to assign to each data set. I'm not sure that Madrigal will do that, but it's something to look into if you want to follow best practices. Basic metadata should be attached to the data always, so at least the authors and the title, that's pretty basic, but you may have other kinds of metadata that are important, like in your case, I think the location, the time frame, and so on and so forth. And then the license should be specified for each data set. So Creative Commons is a website that has a lot of options for licenses. They're all described in a non-legal way. They're very accessible to people like us. And if you pick one of those licenses, you'll be safe. The one that we recommend is CC BY, which means that anyone can reuse it as long as they do attribution, as long as they cite you. There's another one called CC0 where you don't even require attribution, so that's an even better choice. And then the data should be cited in line, and the citation should be in the references. So this is how we would handle data using best practices. Let's look at the software. So the software talks about tables 1 and 2 present a comparison of the implementation of TE and TI, I forget what those are, sorry, between the old and the new model. So the keyword here is the old and the new model. There's no pointer to a specific version or a frozen DOI that gives me that specific version. It just says the old model, the new model. So there's the question about how to access that specific model. One could do it based on years where the model was published or the papers were cited, but the best practice is to be able to cite unequivocally each model and have it accessible online. It then talks about comparing to the IRI model. And so again, there's no pointer to the software version other than the reference that it is a paper that was in 2014. So maybe it's the newest software version from 2016. That's unclear. So the best practice would say that all the software should be in a public repository. You can put your software in GitHub. If you're not a big GitHub fan or you don't like software repositories like that, you don't like version control, we find that many scientists take a long time to learn GitHub. So just zip your files and upload them to a data repository. Data repositories take software. They take, as I said, videos, PowerPoint slides, anything, PDFs, figures, anything. And when you upload your software that way, at least it is preserved and the specific version is preserved. But of course, a proper software repository is where everybody will look for it. GitHub uses Zenodo to assign a DOI to your software. So you can say, give me a DOI for this particular version, and it will give you a Zenodo DOI. They have an API worked out. If you upload your software to any other software repository, proper software repository, it will also give you a DOI. Basic metadata should be attached. So we have a site called ontosoft.org where there's a portal where you can describe metadata about your software. We guide you through many pieces, and then you can take all of that metadata and put it in your GitHub site. The license should be specified. So if you go to opensource.org, they again explain software licenses without legalese. They'll tell you, do you want to have commercial use of your software or not, and whether you want to allow it or not. We recommend Apache version 2 and MIT licenses because they're not constraining whoever reuses your software other than giving you credit. But you can pick any open source license. There's a number of default ones that everybody uses. And then the software should be cited inline, including the version that you're using, and the citation should be included in the references. That's the proper best practice. So here I'm showing these screenshots from the CCMC, and I see that there's data coming in the back. I see that there's software versions in the back, but it's unclear, at least to me from a computational perspective, what version of the software am I using? How am I going to convey to someone the exact selection of data that I did to run the software? So I think that there's more work to be done to make sure that we capture exactly the runs that were done. Also, the models are there, but we need to be able to access older versions, to identify the versions with a unique ID so that we know exactly what version we're comparing. So that's data and software. There's still the question about how the data and the software were put together to create all the figures and all the different results that the paper talks about. So for example, figure 1 shows a comparison of the old model, the new model, and the IRI model. To describe what was done and how that figure is generated, it's a good idea to show the data flow. So we show the same input data going to the 3 models. I don't know if you can see this very well, but the same input data going to the 3 models. The parameters are different for all the 3 models. I don't know if the same ones were used. I couldn't tell. And then there's some comparison code that generates the figure. So presumably that code might be useful if someone wants to reproduce the work. Somebody could rewrite it from scratch, but why make their life difficult when it might be easier to just publish the code that you use to create a figure? The provenance is related to the workflow, but it talks about specific runs of the workflow. So sometimes you do several runs or many runs. This is the case with figures 5 and 6 and 9. So figure 5 shows a comparison between GIDM, IRI, and then observations from Arecibo. And then figure 6, Hikamarka, and then figure 9, Sonderstrom. So it's the same exact workflow, but they're 3 separate runs. And so you want to document for each of the runs if you use different parameters or the same, and if you have any intermediate data that were interesting, that could be useful to others to also publish that. So that's it. Usually we give an author checklist in the PDF of my slides that are in the agenda site of the meeting. You can see extra slides that walk you through each one of these things. They'll tell you a lot more detail about them. There's a 3-hour version, expanded version of these slides on our website where you can see a lot more details. You have that paper that I referenced to look at. But it's basically making sure that your data is accessible, that is documented, including a license, that you have a DOI, that you cited. Same thing for the software, that it's accessible, that it has a DOI, that you're citing it. And then that you document your methods as a workflow, that you annotate anything that you've done manually as a step in that workflow. That you talk about the runs that you did, you document parameters and so on, and then that you identify the authors uniquely, just as you want to identify data and software uniquely. So if you incorporate these best practices into your work, I didn't use these best practices 3 years ago, so I've been learning a lot and trying to internalize what they would mean to our research practice. We follow them continuously now in our work. So I have 14 summer students this year. They all learned about how to do these different tracking of the data, the software, and so on. So when they leave in September, I know exactly what they did. I know exactly where everything is. I'm not going to have any problems building on that work or writing a paper that includes some part of that work. And also, once you track work in this way, it's not just easy to build on that work, but writing the papers in this following best practice is also easier. So I highly recommend that. It's very good research hygiene. So I gave you a lot of best practices. Why should you follow them? Why should you care? Why should you put the extra work to learn to do them and to adopt them and to tell your students to follow them? Or if you're a student, to tell your advisor, you know, I'm going to spend an extra couple days doing this, but it's important, and I'll tell you why. Why? So first, because you want to practice open science and reproducible research. The most cited mathematician in the world is a statistician at Stanford who writes about how he just started to make all their software and data and papers fully reproducible and publishes everything on their website since the 80s. And he says, this is a major reason why people compare their work to ours and why we get cited. We get many more citations because our research is so easy to reproduce. So if you practice these kinds of recommendations, then you'll find a lot of benefits from following this reproducible research. You'll get credit for all of your research products. So if you write software, I see a lot of scientists saying, you know, he does really good plots. You know, I wish I had their plotting software. And somebody else saying, you know, yeah, but I like how you clean your data. You do an excellent job at that. So I think that being able to share those and be cited for doing those things that we don't consider strictly, you know, core research is important. Increase citations to your papers because everybody else will understand them better and understand what you did. You'll write impressive data management plans for your proposals, and people will believe what you write because you actually practice it. You can point them to how you do it. You can extend your CV. So a lot of our authors extend their CV with data and software sections in addition to papers. You can improve the way you manage your research assets when you have a lot of students. Like I gave my example, is much, much easier for me. You can reproduce work that you did years ago and build on it. You can address new funding and new journal requirements very easily. You can attract students that like to do research computationally a lot better. And you can demonstrate leadership by stepping into these future areas. My scientific society, the Computing Research Association, had a document on tenure and promotion that really recognized that current papers are not very friendly to really documenting computational work properly. So I think we're going to see a lot of changes on the way that research is published. A lot of communities are adopting these kinds of guidelines. We didn't invent these best practices. We simply compiled them from organizations that recommend them. So there's a geophysics papers of the future special issue. There's a neuroimaging paper of the future with lots of very specific things to neuroimaging. And we're teaching a lot of scientific paper of the future training sessions. There's a lot more information online on the website. And I'm here all day if you have further questions, so we can discuss some of these topics in detail. Thank you.